Hello, everyone. It is so nice to see everyone this beautiful April afternoon. My name is Jamie Seward, and I am the Senior Associate Director of Alumni Relations with Johns Hopkins University School of Medicine. Before we start our program, I want to encourage you to ask questions by typing them in the Zoom Q&A at the bottom of your screen. It is my distinct pleasure now to introduce our speakers. Lauren Blake is a molecular biophysics PhD candidate at Johns Hopkins with a bachelor's degree in biomedical engineering from the University of Cincinnati. Her thesis work involves building biomolecular tools to control mRNA metabolism and protein synthesis at the single molecule level in living cells. Lauren is a rising leader in the climate tech space after co-founding the Alt Protein Project at Hopkins and mobilizing Hopkins affiliates to join the cellular agricultural movement. Her mission is to obviate the need for plastics and animals in clothing through the biomanufacturing of next-gen biodegradable raw materials for the textile industry, which we'll learn more about today. Lauren is joined by Alexis Peña, who completed her PhD in biomedical engineering at Johns Hopkins in the lab of Dr. Jennifer Ilesel, where they target the immune system to make healthy tissues. Alexis researches human cell tissue products for musculoskeletal injuries and disease. To date, she's co-authored 9 publications spanning regenerative medicine strategies and in vitro cell platforms to ultimately provide tissue engineering and regenerative medicine solutions. Her North Star is improving the quality of life for others, and to that aim, she's exploring climate tech, biomedical, food, and behavioral lifestyle applications of her expertise. So obviously, we have 2 extremely well-qualified speakers, and it's my delight to turn the program over to them.
Well, hello, everyone.
Oops. Go ahead.
Thank you. Yeah, so today our webinar is entitled Biomanufacturing, the Future of Fashion Innovation. And so as Jamie introduced us, we are both technical innovators with backgrounds in biomedical engineering and biophysics. And we wanted to learn more about the fashion ecosystem over the last year. And so we participated in customer discovery courses to talk to these stakeholders and really learn about their pain points and just the processes to go from raw material to final products and what were the considerations for those different steps. And so as you see, we talked to end users, people in sales and sourcing, as well as thought leaders and material innovators to really get to understand the ecosystem. And with that knowledge and our own curiosities and research, we taught an undergraduate intersession course called Future Fashion Innovation, and it was geared towards material scientists and engineers, and we explored how biomedical and chemical engineering technologies can be applied to biomanufacturing in the fashion industry to mitigate some of these challenges that we learned about through our customer discovery. And so throughout the webinar, we're going to be just sharing some of our learnings from these experiences. And so the motivation behind fashion innovation is that our population is growing and is expected to reach 10 billion people by 2050. And so when we think about necessities for human survival, things like food, water, air, shelter, clothing, and energy, we really need to think about how we're going to supply sustainable clothing and shelter for the future. And so what are some of the first things you think about when you hear fashion innovation? You know, we can think about the infrastructure. The fashion industry is ancient and monolithic, and so it's been optimized for a few materials. And so there's this established infrastructure throughout the world, different mills and different equipment for specific materials. And so we can think about what that infrastructure needs to look like so that we can supply clothes to the growing population. We can also think about innovation from the design side. So at the very beginning with designers, thinking about how the material is made, how many pieces, how is it cut and sewn, if it's seamless, as well as thinking about the supply chain. Our fashion industry today is global, and so there are a lot of geopolitical considerations, as well as just timescales needed to ship raw materials and then to process as well as different techniques like dyeing to ultimately get the final product. And so we can also think about efficiencies at the supply chain. And the materials themselves of what our clothes are made out of is also a critical thing to consider, and that's the focus of our webinar today. And so fashion, by definition, is a form of self-expression and autonomy at the particular period and place. And so it's very cultural. And so we can think about our choices in terms of clothing, footwear, lifestyle, accessories, even makeup and hairstyles and body posture are things to think about when thinking about fashion. And depending on where you are, thinking about status, branding is also important for people when they are expressing themselves. And so we are focusing on how to make fashion more sustainable for future generations. And again, we want to focus on the materials themselves. So what our clothes are actually made out of. And so there are a lot of environmental and sociocultural challenges related to the current fashion industry. And so the global fiber production has nearly doubled in the last 20 years, and it has no signs of stopping. You know, fashion brands continue to commit to growth, and they have no self-regulation. And since the 1990s, synthetic petroleum-derived fibers like polyesters have dominated the market. And so plant fibers only have about 30% of the global fiber market, and cotton is the most important currently natural fiber. And then animal fibers only make up about 2%, and then regenerated fibers only 6%. And critically to think about, most of them are fossil based, and there is no end of life solution in fashion. And so when we want to move towards a truly sustainable fashion ecosystem, we need to think about a circular economy. Right now, a lot of the fashion textile processes have a linear economy where they're taking finite natural resources, things that are non-renewable, processing and manufacturing it into a product that ultimately has an end of life where it sits at a landfill or in our oceans and in people's in the textiles for hundreds of years, with like the synthetics taking about 200 years to degrade. And so when we want to move towards a circular economy where we're deriving things that are renewable, that can be composted, and then thinking about feeding those raw materials with things that come from byproducts of other industries, and then engineering those fibers and biotextiles into a truly circular economy so that we can go from finished product and then take that back to a raw material and get an equal product after that. We often think about recycling now, and there are some recycled fibers in the fashion industry, but oftentimes with recycling, you're actually downcycling where the quality is not the same. And so in a circular economy, we want to really be able to go back to that original raw material with the same quality. And so the fashion industry is said to be the second most polluting industry in the world, second only to the oil industry. And it contributes to over 10% of the greenhouse gas emissions worldwide. And as I mentioned, the synthetics take up to 200 years to degrade. And while we are wearing our synthetic fibers or when we're washing them, they actually release microplastics as they degrade and as they wear. And so that's something that is impacting the environment. And polyester alone, again, has been dominating for the last 20 years. And textiles make up to about 10% of landfills. And that has something to do with, again, sort of cultural context of how we think and engage with clothes. And currently, the health implications of microplastics are unknown. Microplastics have been found in human placentas, in lung tissue, as well as in the human blood. And millions of microfibers are released every time we do laundry. Next slide, please. And so the microplastic shedding has the most released from post post-processing. So when at the consumer level, when we are washing our clothes, and right now, a lot of the solutions are consumer oriented. And so I just have a list of a few here, like the Guppy washing bag or the Cora ball. And these things will help to accumulate the microfibers or filter them out or filter out the microplastics. And other fibers also produce and shed these microfibers, but they can biodegrade, whereas the synthetic microfibers can persist in the water systems, can end up in fish and in our ecosystems. And again, we don't know the health implications of this yet. And so I mentioned that cotton is an important natural fiber, and it is biodegradable, but there are some concerns with monocultures and the continued production of cotton related to soil erosion and degradation, things like pollution and water contamination and water scarcity concerns due to the amount of water needed to produce cotton. And so there needs to be continued innovation with natural fibers as well. And so when we're thinking about innovation and sustainability, there are different levels and different contexts and perspectives we can think about. From the design side, there can be a lot of waste at the cut and sew level. And so on the right, this is just showing an animal pelt where there's a lot of waste needed when designing leather hand goods, as well as jackets and apparel. And the material type as well needs to be considered, and thinking about the end of life solution. So what happens when you're done wearing that garment? Where does it go? And we need to think about processes to be able to recycle and reuse clothing, and then to really start with what material we're using so that we does have an end of life solution. And there are also processing considerations. So our clothes often have different dyeing and chemical treatments that are required. And then with leathers, there are different tanning and different processes that have a lot of harsh chemicals that will ultimately end up in our environment. And another consideration is to use valuable byproducts. And so even with things like cotton processing, there can be different byproducts that can ultimately be used for a valuable product. And so thinking about how can we use byproducts from different processes to ultimately create new and valuable technologies and products. And so thinking about the sociocultural impacts of the fashion industry and the reasons for this overconsumption, it's definitely been a different cultural shift. And so our demand for clothes has grown tremendously. There was a time when no one had closets because people only had a couple of garments. And now it's common for people, to convert a bedroom into a walk-in closet. And so consumers have driven a lot of this demand for clothing, and also the desire to have new clothes and to quickly have clothes in the secondhand market. And so a lot of our clothes that we end up donating ends up in this secondhand fashion market in other countries, like in Accra, Ghana, in the Kantamanto market. That's one of the second largest clothing markets in West Africa. And so they get 15 million garments weekly. And to put it in context, their population is 30 million. And so most of these clothing that are coming into these markets are actually discarded due to poor quality. And the largest exporters into these Kantamanto market are the UK, Canada, USA, Netherlands, and China. And they have female head porters that have to carry hundreds of pounds of clothing up to a mile for less than $1 per trip. And I just have a quote on the next slide, thinking about waste and greed. And so waste and greed are two sides of the same destructive path. Fashion loves to emphasize the material consequences of the industry, but swapping one material for another is transactional and not transformative. And so even though the materials itself are important, if we don't change some of the cultural implications and the cultural demands, we're not going to transform the industry. And so secondhand clothing waste is a public crisis. And as I mentioned, in Ghana in particular, they're getting millions of tons of these garments annually, and they end up internalizing this waste, and they themselves feel filthy and dirty. And so we really need to, again, rethink the fashion ecosystem. And just to highlight some other challenges in the apparel industry, things like resources depletions, climate change. There can be some animal welfare concerns, as well as human welfare concerns as well, and like human labor concerns, as well as water pollution. And the demand for agriculture for textiles can lead to food insecurity, things like air pollution and habitat destruction are all things we need to continue to think about and innovate away from. And so for the next part of the webinar, we just wanted to give a landscape of the past and present textile industry. And so in general, the textile fibers are divided into natural and man-made categories. So you can see with the natural fibers, they can be further stratified into animal, vegetable, or microbial derived fibers. And there's some examples of each below. And then for the man-made fibers, they can be regenerated, synthetic, or mineral. And they all have different characteristics and applications. And often in fashion, because there are stringent requirements for things like abrasion resistance and elasticity, many of our clothes are actually mixed composition fibers. And so it'll have percentages of all of these different, or any combination of these different fibers to get that ideal characteristic. And for some examples of natural cellulosics, things like cotton, linen, and bamboo rely on traditional plant agriculture. And typically for these natural cellulosics, they're generally staples. So there are different lengths of fibers that are then spun into long fibers that can then be used in fabrics for garments. And generally cellulose is mainly used to produce paperboard and paper, but also generally cellulose for industrial use is mainly obtained from wood pulp and cotton. And when thinking about the man-made cellulosic fibers, these are actually made of dissolved cellulose from trees. And so these are renewable resources, generally like eucalyptus, wood pulp, bamboo, and fruits are commonly used to get the cellulose and can be spun into long filaments. And they generally require less post-processing than cotton and a quicker turnaround. But there are some challenges related to these man-made cellulosic fibers, such as monocultures. Generally, when we have agricultural systems that are in monoculture, they can be susceptible to disease that will end up wiping out that whole monoculture, and that can be devastating for the environment as well as the harvest for the downstream application and products. And this process, although it's coming from a renewable source, it is semi-chemical because it requires harsh chemicals for dissolving into cellulose. And as I mentioned, it does have to be blended and combined with synthetics for those desired properties. And there are also protein-based textiles, which are generally reliant on animal agriculture, and depending on that agricultural system can have some environmental impacts. And so we have to think about the agricultural systems used for the production of these raw materials as well. And a lot of these processes require chemicals as well, like with leather tanning, and with the silkworm silk processing, it's very tedious and artisanal. And basically the larva is also sacrificed during the processing of silk. And synthetics are fossil fuel based, and generally the industry is reliant on synthetics because it does have modular applications and desired features. And they are made from synthetic polymers, which come from oil, coal, and other petroleum-based chemicals. and then generally polymerized into long filament strands, unlike natural fibers where I mentioned they're like short fibers that have to be spun together. With this process, they're able to be extruded in long filament strands. And I just wanted to highlight this phenomena that occurred in the 1940s and 50s at the advent of industrial synthetic fiber production. And so until the end of the 1930s, most women's stockings were actually made from silk. And generally, these 3-threaded silk stockings only had about 150 hours of wear. And so nylon was able to, withstand and have longevity compared to silk. And so women were running to stores, and they called them like nylon riots, because they wanted to have these stockings, because during the war, nylon was classified as an essential material. And so there were clothing rationings, and so women even ended up just like cosmetically sketching these lines to appear like stockings. But nylon definitely disrupted elastic applications like women's stockings. And so when we think about what's needed for adopting next generation sustainable materials, we have to think about some of these challenges. And so, as we alluded to earlier, synthetics cause many problems for the environment. And we have to think about the benefits and why the industry is reliant on synthetics. So synthetic materials are generally cheap. They are more durable and strong. They are fast dyeing. And they usually have better affinity to dyeing. And so at the chemical dyeing processes for textiles, a lot of waste occurs because not all of the dye binds to the material. But generally with synthetics, they have faster dyeing, and they also maintain the color better. And fashion stakeholders really require that the color stays consistent over time. And that is unlike natural fibers with over time. I'm sure you noticed if you have like a cotton t-shirt, maybe that color fade, like with black in particular, can fade over time. But with synthetics, it will maintain that color. And synthetics also have minimal processing. And so, again, it can be extruded into these long filaments, which is desirable. And then it has these flexible applications. And now with the dominant athleisure and athletic apparel, stretchiness and elasticity is actually a really critical feature of textiles. And synthetics do have a reliable supply and a reliable harvest season. So with raw materials for natural fibers, again, there can be some things related to unpredictable weather and contamination that can impact the raw material for natural fibers that we don't have to deal with when we're producing synthetic fibers. And they also have less shrinkage during washing and drying. And we wanted to just highlight some insights from the fashion stakeholders that we talked to during customer discoveries. And broadly, fashion brands realize that, the raw material choices do contribute most to the industry's deleterious environmental impacts. And so the industry in general, and also regulation, is moving towards rethinking these raw material inputs. Brands do want to use more sustainable materials, but there are no robust solutions that exist that keep up with customers' demands for clothes as well as costs. And so after our conversation, we found that, the cost of the fibers was really important when sourcing. And so thinking about options that are competitive pricing with current synthetic fibers will be critical. And then we need innovative new technologies to mitigate the negative impact of the increased demand of clothing, as well as, again, as we mentioned, innovate away or rethink some of these cultural trends of needing and over-consuming clothes.
Thank you so much, Alexis, for setting up the next section really well. So again, I'm Lauren Blake, and I'm going to introduce some of the innovations that have been ongoing in this space to produce a more sustainable fashion economy. So Alexis set up the conversation really well in talking about the environmental impacts and the sociocultural impacts of the current fashion industry. And so I wanted to highlight some of the main methods for producing next-gen materials in a more sustainable or circular fashion. So synthetics are still not out of the question. Again, Alexis mentioned that they could still be partially recycled, or they could also be derived from renewable resources such as genetically engineered microbes that have been engineered to produce some of these synthetic polymers. And then there's also plant-based methods where you're using traditional plant agriculture to derive, more complicated plant sources, like this kapok tree that serves as a nice insulation alternative. A cotton alternative cannot be in a fluffy insulative shape such as this, but there are other plants out there that can be harvested to replace some of these synthetic or animal-based fibers. So fermentation is another major element of the next gen material innovation. And that's probably what we're going to focus on for the majority of this talk, because this is a biomanufacturing focused talk. And fermentation essentially means, it can mean producing alcohol using microbes, producing food ingredients using microbes, biofuels, and we'll be talking about it in the context of making biomaterials for textiles today. And also stem cells, that this is a growing technology in tissue engineering as well as cultivated meat. And people are starting to look at stem cells as an option to biomanufacture sustainable textiles as well. And before I get into all of these different innovations, I first want to introduce you to the other major topic of our talk today, which is biomanufacturing. So what is biomanufacturing actually? Biomanufacturing, by definition, is a type of biotechnology that uses biological systems to produce commercially important biomaterials or biomolecules. And this can be in the context, again, in medicine, food and beverage processing, or industrial applications such as textiles. And so biomanufacturing involves the recovering of these products from natural sources, such as cultures of microbes or animal cells or plant cells. So it's not just fermentation, though that seems to be a very promising pillar of biomanufacturing. And the cells used during the production are usually either naturally occurring or they can be derived using genetic engineering techniques, which we will discuss next. So recombinant DNA, or genetic engineering of microbes, was invented in the 1970s. And so it was partially invented initially as one of the first applications of recombinant DNA was to address diabetes patients. So how recombinant DNA works is you have an original organism, in this case, a human, and their pancreas is failing. So the desired molecule that you need, that's usually secreted by the pancreas, is insulin. But instead of getting this insulin from a pig pancreas, which is how they used to deliver these therapeutics and manufacture them, you could genetically engineer a yeast microorganism that can produce this insulin molecule much more efficiently. And so finally, your final product is a diabetes treatment in the form of therapeutic insulin. And recombinant DNA has also been hitting the food industry. It's been hitting the food industry for a while, but I'll just highlight one more recent innovation You may have heard of some new technology to grow whey protein from a cow in a microbe such as filamentous fungus to produce non-animal dairy ice cream or milk or cheese or what have you. So therapeutics and food are two examples of where recombinant DNA and genetic engineering has really hit biomanufacturing. And the way that recombinant DNA and genetic engineering works is essentially you're taking the DNA from one organism and placing it into another. So you have a DNA of interest, whether that be insulin DNA or the DNA to express the whey protein or a spider silk protein, for example. And you enter that, you place that DNA of interest into a plasmid to obtain a recombinant DNA, recombined DNA, and then you insert it into your organism of choice. And this has been going on a lot for proteins and protein biomanufacturing. And so I really wanted to highlight some of the advantages of proteins in the textile industry. Proteins are renewable and biodegradable. And also, as it relates to the textile industry, they also have a lot of unique chemistry that makes them better at absorbing dyes, as well as preventing flammability, reducing flammability, or moisture absorbing, which is, of course, very relevant to performance textile industry. They can be strong and elastic, especially if you're thinking of proteins like spider silk. And most importantly, they are tunable with protein engineering advancements. And so if you think about proteins compared to cellulosics are also renewable and biodegradable, and they can also absorb dyes and moisture, but they cannot be engineered to such a great degree as proteins can be. There's only so much you can engineer about those enzymes that produce cellulosic fibers in order to confer different proteins such as strength or elasticity. But protein engineering is one of the reasons that proteins are such a promising new frontier. And so I wanted to highlight a few different proteins that can contribute to the textile industry specifically. So genetically engineering organisms to express this recombinant DNA can contribute to many elements of the fashion industry, such as, I mentioned dye absorption too, but the proteins can also be just a dye themselves, such as this red fluorescent protein that is usually found in a coral organism. And you also have green fluorescent protein found in jellyfish that is now used in all kinds of applications. But this protein can be expressed in microbes to have a naturally dyed fabric instead of all these harmful chemicals that often dyes are made of. You can also use recombinant DNA to express spider silk and grow that in large quantities to potentially produce Kevlar replacements. Or there are also elastic proteins. So elastic proteins from connective tissue found in oysters, for example, can be combined with existing textile applications and potentially be a spandex alternative. And this is really critical, especially as spandex is one of the few materials out there in textiles that is absolutely not recyclable at all by any current methods. And of course, people are trying to work on that, improve the recyclability or find ways to recycle spandex, but as of now, it is not possible to recycle spandex. And it is also very difficult to separate from garments currently. And I mentioned whey protein from cows in the context of food before, but there's also some fun research going on about beta casein, which is typically found in cow's milk, being produced to confer a water repellent property to, for example, rain jackets, so that you don't have to use these synthetic polymers. And so there's a lot of different exciting applications for these proteins. And it's not just proteins, there could be other small molecules or, even dyes that are produced in these genetically modified organisms that are not protein derived, maybe just a pigment, or there are synthetic polymers that could also be produced, but proteins tend to be a really exciting frontier, as mentioned earlier. And so I wanted to go into some of the details about how you would go about amplifying this protein in a microbe and then separating it from the rest of the microbe. So this is a somewhat cost and energy intensive process still. And the genetic engineering, of course, you're going to have some screening that might occur, as well as the actual genetic engineering of the microorganism, which usually once you have decided on what protein you want to express in your microbe, it's pretty straightforward from there. You only need to do it once. So that's less energy intensive. But where it starts to get a little more energy intensive and resource intensive is in the industrial cell culture process, where you are trying to amplify your genetically engineered bacteria in large amounts. And therefore, you're amplifying your protein, your fibrous protein, for example. And then after this, you need to separate the protein of interest from the bacteria. And this can involve a series of downstream purification steps, drying steps, as well as just purifying steps. You need to purify the protein from all the bacterial components and media components. And one white space area in this is finding ways to get the protein to secrete out of the bacteria so that you do not have to open up the bacteria and kill the bacteria in that sense, just thus wasting all of that energy to grow the bacteria. So secretion steps instead of bacterial lysis are one example of where this process could be improved for scaling up. And then finally, this is the downstream processing for a fiber specifically. But protein-based materials can be spun, and this is sort of like a process that mimics a spider's spinneret. It's like an artificial spinneret system where you align the fibrous proteins through a laminar flow, and then you have your strong fiber at the end. And so this is a sort of just general schematic of how the process would work. And there is a lot of R&D going into how to improve this process at every step of the way, not just for textiles, but for biomanufacturing of drugs and food and other biomaterials. And one interesting strategy for scaling up that the DOE has a strong focus on right now is to find ways to have cheaper feedstocks so that you can grow the bacteria in a cheap way, because this bacteria has to eat something, and therefore you want to find the cheapest way to feed these bacteria so that they can grow. And DOE, the Department of Energy in the US, their focus is on lignocellulosic feedstock as an alternative carbon source to glucose. Typically, if you are in a molecular biology lab and you're growing proteins, doing protein purification, you'll often use a urea broth that has glucose in it, but glucose in itself is actually a very expensive, relatively feedstock for growing these proteins on a massive level. So we have to look at other sources of feedstock, and lignocellulosics happen to be the most abundant renewable bioresource material available on Earth. That's because lignocellulosics are primarily composed of cellulose and hemicellulose and different lignins, which have all these carbon sources, and they can be converted into energy for bacteria, for example. These lignocellulosics are found in grasses, trees, and agricultural residues. And that's one of the reasons that they're that they're most abundant. And the DOE is trying to focus on engineering bacteria that can thrive very well on this feedstock. So recombinant spider silk, as I was alluding to earlier, it's been a hot topic since about 2007 when Spiber, a company, biotech company, was founded in Japan. So here's an example of some of these wet spin spider silk proteins. And there have been many companies that have been attempting to create a very strong wet spun or electrospun, or even just a composite material made of spider silk. They've had various degrees of success. And I think as of late, there's been yet to be a commercial application. Actually, I take that back. Just a couple weeks ago, Spiber announced a collaboration with North Face, and they are actually starting to sell some jackets made from a small percentage of their spider silk protein. And there's still a lot of innovation and upscaling work that needs to be done in order to scale up and make this spider silk, this recombinant spider silk, cheaper. These different companies are using different organisms, so it's been interesting to see how these have scaled for each one. Some companies are using E. coli, some companies are using yeast. Spidey Tech is actually growing their spider silk in alfalfa plants and then using traditional plant agriculture to extract the protein. Craig Biocraft Laboratories has genetically engineered silkworms to produce spider silk proteins instead of silk fibroin. And then they're just using traditional silk agriculture that is traditionally dependent on like mulberry leaves as a feed source for the silkworms. And yes, we really look forward to seeing some more products out of these companies. And there have been other companies, such as this company called Werewool, that they've been really focusing on using proteins and dyes made in genetically engineered microorganisms. Here they're showing a green fluorescent protein that's being expressed, and that's from a jellyfish that was purified and added to some alginate fibers. And so this is a very interesting startup out of the Fashion Institute of Technology. It's led by Thean Shiros, a professor there. And there's been some other developments, such as bacterial dyes that are produced by microorganisms. Here you can see a jet dyeing, here you can see the microbes that are making this green-blue dye. And then they're sent through a jet dyeing machine, and you can see the final dyed swatches. It actually looks like a really nice indigo, potentially a dye replacement for blue jeans. And just highlighting a few other developing technologies. There's bacterial nanocellulose that can be biomanufactured and harvested to produce bioleathers. This is a proof of concept that was done by a group at the Fashion Institute of Technology. And you can see, I don't know if anyone's ever tried to grow kombucha themselves before, but kombucha is usually a symbiotic culture of yeast and bacteria, and it sticks together really well because of all the nanocellulose that it's producing in the extracellular matrix. And as it turns out, this kind of material, it could be used for leather, but it could also be used for alternatives to man-made cellulosics. And so man-made cellulosic fibers are starting to get a new look, and I wanted to highlight a few different technologies by different companies out there. So a company named Modern Synthesis recently developed this proof of concept. It's actually a shoe where bacteria had grown around it and secreted some cellulosic material, and so they call it a microbial weaving process. And then they remove the cellulose from the scaffold, the original scaffold that the bacteria was growing on, to have this shoe. So it's still in a proof of concept mode, as a lot of these technologies are, but it is a very promising technology, and it's, of course, renewable and a potentially circular. There's also another company up in Boston that is developing lab-grown cotton. And what they're trying to do, it's a little bit different. They're actually using the cotton plant. And because cotton plants tend to be totipotent, meaning they can differentiate into any downstream feature of the plant that they want with the right conditions. Galley is trying to replicate the unique differentiation events that occur to make a long, thin cotton fiber, and they're trying to do that without having to grow the entire plant. So it's a pretty complicated process, and I think they've been able to get cotton fiber cells to grow to a few millimeters, or at least a millimeter last time I checked. And so definitely a company that would be interesting to follow. I mentioned leather before, and I wanted to highlight a few other alternatives to leathers and also exotic skins. There is a mycelium-based leather called Milo, which I'll highlight again in the next section, and a stem cell-derived leather made at Vitro Labs. Again, they're trying to actually differentiate stem cells of a cow and get it to differentiate into something like a skin cell. And it's a very complicated process, but because of advancements in tissue engineering, this company has been able to make some headway. And there's also fruit waste derived. Peña has a system where they are using recycled pineapple to produce a pineapple leather. So some very exciting technologies. And I wanted to quickly, in the last few minutes before we do Q&A, I wanted to do an industry overview of current trends. So the next gen material industry is rapidly growing, and I wanted to give this little snapshot from the Material Innovation Initiative's State of the Industry report on next gen materials that was made last year. And here's the state of the industry of the next gen material industry at a glance. There has been over $1 billion invested from 2015 to 2021. And I mean, these are just, I won't go through all of the numbers here. It's a really great report to read, and it will really get you hyped up about next gen materials. But there are a growing number of companies in this space, and I just mentioned a few, and lots of new investors, and also lots of new technologies. People are using mycelium, they're using blends, cultured animal cells, recycling, microbe-derived, and most are using plant-derived, actually. It turns out that 38 out of 40 leading fashion brands are actively searching for next-gen materials. And so these companies, these fashion brands, happen to be a big stakeholder in the next-gen material innovation business. And there have been some interesting collaborations. One was just announced, or the product of one was just announced a couple days ago. So you can see this is a very exciting time to get into this space. In 2021, Lululemon partnered with Biomedical, it's a sustainable materials biotech company, to engineer microbes to produce nylon biologically instead of from petrochemicals. And in 2021, also, Adidas partnered with Bolt Threads to implement their mycelium-based leather product, Milo, into their new Stan Smith shoe. And so both of these, since the partnerships began, have recently announced new product lines. And actually, I think the synthetic nylon is just as expensive, or just as, yeah, it's pretty expensive at Lululemon, just as expensive as the other t-shirts that they offer made of traditional fossil fuel-based nylon. And as it turns out, the US government is also actively investing in R&D for biomanufacturing of biofuels, food, and biomaterials. I wanted to point out this executive order that was signed back in September 12th of last year on advancing biotechnology and biomanufacturing innovation for a sustainable, safe, and secure American bioeconomy. And the Department of Energy's Bioenergy Technology Office, BETO for short, is aiming to support these efforts to produce viable biofuels and bioproducts using these sustainable sources of biomass and waste resources. And like I said before, they are focused on finding microbes that can thrive off of those lignocellulosics. Government policies are also popping up around the US and globally to promote sustainable fashion practices. There is trending regulation towards a circular fashion economy. In Europe, they're trying to make textiles long-lived and recyclable, and to a great extent made of recyclable fibers by 2030. There's a New York Fashion and Sustainability Social Accountability Act that includes identifying and taking remedial action to address adverse impacts to human rights and the environment. And there's also the Senate Bill 54 in California, which is calling on the state to reduce plastic consumption and packaging and be more responsible about plastic, which includes plastics in our textiles. And so this is putting added pressure on to different companies and fashion brands so that they must start to make changes and adopt some of these next gen materials. And lastly, I just wanted to point out a few different resources. The Material Innovation Initiative is a nonprofit organization, and they're focused on replacing animal and petroleum derived textiles. You can reach out to them or Sydney Gladman specifically on LinkedIn to find out about all their resources. And I'll go through this last part kind of quickly so that we can get to the Q&A. But yeah, just focusing on how you can make a difference personally. You can donate to various organizations who are promoting sustainable textiles like Fashion for Good, Textile Exchange, Biofabricate, Material Innovation Initiative, Ellen MacArthur Foundation, and many others. And I encourage you to learn more. You can read these reports that are written by various nonprofits or consulting groups, and you already have a good start because you've come to our webinar. There's different lifestyle changes you can make, such as buying less clothing, buying secondhand, purchasing long-lasting and recyclable biodegradable clothing. I want to point out that sustainability is a series of compromises, and that we always need a lot of people doing some things better rather than a few people doing everything perfectly. So any changes you can make personally will be helpful. If you're a student or at a university somehow, you could sign up for relevant classes, advocate for new courses, start an interest group or join one that exists already, or you can conduct research in a PI's lab. And I'm just highlighting some pictures from our recent course where we did alginate fiber extrusion and spider silk extraction. There are so many different disciplines that can contribute to sustainable fashion innovation. And here's just to name a few. And it's definitely not a complete list, but there is room for everyone in the sustainable fashion industry. And with that, I'll leave up our LinkedIn's, and we encourage you to reach out to us or email us with any questions and connect with us, follow us, whatever you want to do, and would love to take anyone's questions right now. Looks like we have a couple questions in the Q&A already. Thank you, Christopher. And So Alexis, you're able to see the Q&A as well too, right?
Yeah, I answered Lewis's question. I wonder, can everyone see the answer to that? I typed it, but we
It
can
may-
go over it
It may
too.
be helpful to say it out loud because the rest of the audience can't see the questions.
Okay.
Sorry.
Yeah, so there was one question about sustainable solutions for yarns within knitwear. Elle has heard about alginate, but would like to know if we've seen any in the US or overseas, and that testing the textiles to see if they can hold up during development is crucial when trying to rid ourselves of toxic materials. And there are various certifications that brands can do for their processes to ensure sustainability and like ethical considerations, but sometimes those are costly, and so they can be prohibitive as well. But that's something to look at. And I know like Mara Hoffman, Eileen Fisher, Stella McCartney are major players that really think about sustainable sourcing and throughout their whole supply chain. But in terms of your question, right now there are a lot of next gen material fibers that are made from byproducts or waste. And we mentioned man-made cellulosic fibers in our presentation, and those are meant to be a more sustainable option in knitwear. But there are some companies like AltMat, they're developing fibers from residues of foods and medicinal crops. Their fiber, they're doing a novel hemp cottonization process to make cotton-like hemp fibers. And there's also these cupro fibers that are like silk. They're made from pre-consumer cotton waste. So yeah, people are thinking about how to use these byproducts and waste to make things for yarns too.
I can go ahead and answer Christopher's question. So Christopher asked, what are the greatest barriers to entry or barriers to scale for the industry? How long before smaller businesses can use some of these technologies at affordable cost bases? And yeah, it's a really important, critical question. I can give you some of my thoughts on it. I don't have exact numbers, but regarding what are the greatest barriers to entry to scale for the industry, right now, a lot of these fermentation-based methods are not highly competitive with, for example, synthetics. And one of the reasons is because of the high cost of the feedstocks and the high cost of the downstream processing. So one of the things that we've learned in a good strategy to enter these industries is to enter high value markets first. So you're probably not, if you were wanting to enter this industry, you would not want to start off trying to sell a product to H&M, who's trying to sell a t-shirt for $3. But there are many companies, especially in the eco luxury market, or just lots of companies whose pillar is sustainability, and they tend to sell like slightly pricier, high value products anyways, like Max Mara, Patagonia, just to name a couple. And so it's good to partner with, it would be good to partner with companies like that. North Face is another one who Spiber partnered with. And you also would need to be willing to sell your product in a small amount. So I think a lot of these companies or these startups in this space are selling their products in amounts of maybe 3 to 10% maybe. And that way you can sell the product at a premium, but you're not using as much product, you're not using as much of your own product in the final product. And that can help companies just get into the market while they're scaling up. And then you asked how long before smaller businesses can use some of these technologies. And so if you're referring to the startups, I'd say we're probably about 5 to 10 years away, especially with all this prioritizing of biomanufacturing innovation. And we're already starting to see businesses in the fashion industry, fashion brands, the big ones, not the small ones yet. They're starting to adopt these next gen materials in their clothing lines. So that's already happening, but it'll probably be, it'll take a little while for the masses to start adopting as well. We're still in the early adopter stage. Yes, I hope that answers your question. And I don't see any other questions, but so Alexis, if you have any other things to add.
No, I think it's that was everything. There were no more questions and we're at time.
We're so happy we had you. This was so wonderful and engaging, and I really appreciate your time and your talent. We will send a follow-up email with a recording of the program, along with a list of resources and our event schedule. And if there's anything you want to share with the audience, your slide deck or whatever, just send it to me and I'll send it out to everyone. But in the meantime, thank you. We do have a raised hand. If you could type your question in the Q&A, that would be great. Oh, it looks like maybe we have a few more. I mean, I'm okay to, very helpful. Can you talk a little bit more on stem cell based fibers? Do you want to talk about that real fast and then we'll wrap?
Yeah, I can go into that. That was actually something Alexis and I, both being from biomedical engineering backgrounds, were really intrigued by initially, is the stem cell approach. But we quickly learned that the field is not really ready. Oops, did my screen just disappear? We quickly learned the field is not really ready. Where did I put some of those? And it still takes many months to produce some of these skins and hair products made from stem cells. We were following a company called Furoid, who was attempting to make stem cell based fur, and it took 6 months or so just to get like a millimeter fiber, or a little millimeter hair. And so it's still a ways away. That's why we think some of these other microbial based methods and plant-based methods are probably a little more promising, but I definitely think stem cell derived methods will play a part. It's just one of the reasons that it's harder to do than cultured meat, which is a stem cell derived method, is because cultured meat, it's challenging in itself, but you're producing the tissue, whereas if you're making lab grown skin or stem cell derived skin or fur, that is actually, you have to make an organoid. It's similar to it's an organ. Skin is an organ, hair is an organ. You need a lot more accurate biology to differentiate the hair follicle and the skin epidermis to the precise characteristics that it needs in order to mimic a leather or a fur, for example. So it's just it's a little bit further away because we don't fully understand all those differentiation pathways, and there's a lot of growth factors involved, differentiation factors involved, which are really expensive.
Yeah, I'll just add that definitely is, very complex and costly, and people have moved to like other just cell derived methods, especially for like leathers. And so there are companies or startups that are working on like fibroblast cultures to produce the collagens, and then thinking about like electrospinning and the organization of the collagen that the fibroblasts are producing for some of these materials. Well, thank you, everyone.
Well,
Thank you so much.
Have a wonderful afternoon, and thanks again. And hopefully we'll see you soon, and we'll see all of you at our next webinar. Thank you so much. Take care.
Thank you.
Bye-bye.